Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials subject. In this subject already we have covered all theory related topics like simple stresses and strains and shear force and bending moment diagrams and simple pure bending theory and torsional stresses. Now in this session, I want to discuss about question bank. So the topic is Euler's column theory. So already we have discussed about columns and struts topic. So in this topic we have derived the equations, Euler's equation, and we have learned buckling load and crippling load and various columns, so end conditions also we have seen. Now in this question bank, so how to attempt the question in examination, so how to write and how to apply the formulas whenever the columns are subjected to some loads, we will see in today's session. So first of all, the outcome of this topic is the student should be able to analyze the Euler's column theory and deformation of columns and struts. So how the columns and struts will deform under loads and how to analyze this Euler's column theory. So we will study in this topic, already we have seen, so that after completion of this topic the student should be able to analyze all these things. So that is the main aim of this outcome. So Euler's column theory, the question number 1, these questions taken from question bank, define column and struts and also explain failures of columns or struts when it will fail. So first of all, how to write the definition of column and the definition of struts and then explain failure conditions, so when they will fail. So that is the first bit. In second part, explain briefly about Euler's column theory. First you have to write the columns and strut definitions and failures and then briefly you have to explain the Euler's column theory. What is this theory? So what are the applications of this theory? You have to explain briefly. So this is the question. So now we will see the solution. A structural member subjected to an axial compressive force is called a strut. As per definition, a strut may be horizontal, inclined or even vertical. Suppose you take this structural member. So axis, one end is fixed, subjected to compressive force. It may be horizontal and it may be vertical, it may be inclined, even vertical, horizontal and inclined. So example, connecting rod, piston rod, etc. Clear? So next one, The failure of column or strut. I have seen the compressive force is called the structural member whenever subject to an axial compressive force is a strut. So what about column? So whenever these short dimensions structures are called struts, the long structural member are called as columns. Now, failure of a column or strut. It has been observed that when a column or strut is subjected to some compressive force, then the compressive stress induced. So you know the compressive stress. So load per area. Where load is compressive force and the cross-sectional area of the column A. If the force or load is gradually increased, the column will reach a stage when it will be subjected to the ultimate crushing stress. So here, if the force or load is gradually increased, so the column will reach a stage, the crushing stress stage. So already you know as per stress strain diagram, after this ultimate crushing stress, if you are increasing the load, gradually increasing the load, what will happen? Failures occurs beyond this ultimate crushing stress. So beyond this stage, the column will fail by crushing. So the load corresponding to the crushing stress is called crushing load. A compression member does not fail entirely by crushing, but also by bending. That is buckling. So this happens in the case of long columns. The short columns, okay, compressive. So suppose the length of the column is very short whenever this is subjected to compressive load. What about the long columns? So the long columns bend like this. So this happens in the case of long columns. So all the short column and long column fail due to their crushing. But if a long column is subjected to compressive load, it is subjected to a compressive stress. See the failure of column or strut shown in this figure. So the column due to the bending load or crippling load. Up to ultimate crushing stress, there is no problem. Beyond this ultimate crushing stress, the column will fail. So that the struts are always does not fail due to the crushing. Sometimes happens due to the buckling load. So if the load is gradually increased, the column will reach a stage, that is when it starts buckling stage. So the load at which the column just buckles is called buckling load. So whenever the column fails, the corresponding load is called buckling load or critical load or crippling load. And the column is said to have developed an elastic instability. Instability, the column is said to be elastic instability. So for a long column, the value of buckling load will be less than the crushing load. Moreover, the value of buckling load is low for long column and relatively high for short columns. High for short columns and the buckling load is low for long columns. So these are the failures of columns and struts. So here see, you can see here failure of a column or strut. So the buckling and due to compression and shear. So here see, the for long column, the value of buckling load will be less than the crushing load. The buckling load is low for long column and high for short. This is very important. So see in this figure shown this type and the column due to the buckling load the column. So the middle portion between the floor and the roof is called a structure member, that is column or strut. So this type of failures will occur in columns due to the crushing load and due to the buckling load or crippling load. Now the second bit, the B portion, Euler's column theory. Explain briefly about Euler's column theory as asked. So up to here we have seen, we have learned column and struts definitions and failure conditions of strut and columns. Now what is this Euler's column theory we will see here. So the first rational attempt to study the stability of long columns was made by Mr. Euler. So he derived an equation for the buckling load of long columns based on the bending stress. So while deriving this equation, the effect of direct stress is neglected. This may be justified with the statement that the direct stress induced in a long column is negligible as compared to the bending stress. So here direct stress is neglected while deriving the Euler's column theory. Next, assumptions in the Euler's column theory. Some assumptions made while deriving this Euler's column theory. The following simplifying assumptions are made in the Euler's column theory. So one is, initially the column is perfectly straight and the load applied is truly axial load only. The cross section of the column is uniform throughout its length. There is no interrupt changes in their dimensions. Throughout the section is uniform. The perfectly straight, the load applied is truly axial load. The cross section is uniform throughout its length. The column material is perfectly elastic material, homogeneous and isotropic and obeys Hooke's law. These are the assumptions. Elasticity property, whenever remove the load, it regains its original shape. Elastic property. So this property is called elasticity. Homogeneous and isotropic. It shows all same uniform properties in all directions. There is no change. The material constant, the elastic constants also fixed and obeys Hooke's law. Hooke's law, the stress is directly proportional to strain. So stress is equal to E into epsilon. So E is equal to sigma by stress by strain. So the column material is perfectly elastic, homogeneous and isotropic, and thus obeys Hooke's law. So these are the assumptions, and two more assumptions also there. The length of the column is very large as compared to its cross-sectional dimensions. The length of the column is very large. The length is large when compared to this diameter. Length greater than diameter. So this is diameter. So the column, the length of the column is very large when compared to D. See, the shortening of column due to direct compression being very small is neglected. So due to the direct compression, so direct compression stress load per area, it is very small. So that's why you may neglect. The failure of column occurs due to buckling alone. So these are the assumptions. The failure occurred due to the buckling. Now, the sign conventions are very important. So there are different signs used for the bending of columns in different books. But in this, we shall follow the following sign conventions which are commonly used, international recognized. So negative sign means concavity. Positive sign, convexity. Convexity shape and then concavity shape, already shown in this figure. For concavity shape, always use negative sign. So negative sign means indicates it occupies concavity shape. The positive sign indicates convexity. So the types of end conditions of columns, so very important these conditions. So in actual practice, there are number of end conditions for columns, but we shall study the Euler's column theory on the following 4 types of end conditions, which are important from the subject point of view. So based on these end conditions, how to derive the buckling load formulas. Euler's column theory, how to derive. So what are the end conditions? First, both ends hinged. The second one, both ends fixed. One end is fixed, other end is hinged. Third one. Fourth one end is fixed, other end is free. So these are the 4 conditions and conditions of the column. So based on these conditions, we have to derive the equations. So I will show you one condition here, how to derive the Euler's column theory, Euler's buckling load formula. So in this, the first one is both ends hinged. So both ends hinged means, suppose you take one column. So ends are hinged here, not fixed. And then both ends fixed. And one end is fixed, other end is hinged. The bottom end is fixed, other end is hinged. And one end is fixed, the other end is free. The columns with both ends hinged here shown. The first you have taken the both ends hinged. Hinged ends, these two are. One end is hinged and one end is fixed. one end is fixed, the other end is free. Next case. So first we will see the columns with both ends hinged. So in examination, first we explain the Euler's column theory and then take any one condition. So here I have taken columns with both ends hinged. Consider column AB of length L is hinged at both of its ends, A and B, and carrying a critical load at B. As a result of loading, let the column deflect into a curved form AX1B as shown in figure. Now consider any section X at a distance X from A. See, let critical load on the column. Let P is the critical load on the column. So here take this column, both ends are hinged at A and B. So the deflection Y is deflection of the column at X. Take X section here with the distance X. So the deflection is Y. So the first one is before deformation AXB. So after applying load AX1B. So that is here written. The column deflect into a curved form. Curved form, that is AX1B. So the moment due to the critical load P, that is minus P into Y. So the minus sign due to concavity towards initial center line. So here, so the moment due to the critical load written, the critical load on the column multiplied with deflection of the column at X. In this case is columns with both ends hinged. See, here use the bending stress equation EI into d square y by dx square plus p into y is equal to 0. So the deflection formula EI into d square y by dx square plus p into y. So p into y is the movement due to the critical load. So now simplify this equation, d square y by dx square plus p by EI into y is equal to 0. So auxiliary equation m square plus p by EI is equal to 0, m square is equal to minus p by EI. So you can write, so the m is equal to minus, m is equal to square root of minus p by EI. So here complex number solution shown here, the m is equal to plus or minus I into p by EI. So here m is equal to minus square root of minus p by EI. So negative sign. So it gives roots complex numbers. So that is plus or minus square root of p by EI. So that is equal to, you can write alpha plus or minus I beta. The general solution of complex numbers is E into e to the power of alpha x inside bracket c1 cos beta x, c2 sin beta x. So here, see the c1 and c2 are constants. How to calculate these two values by using initial condition. That means boundary conditions. So therefore, the y is equal to c1 x into square root of p by EI and c2 sin x into p by EI. So the beta value is substituted square root of p by EI. So where C1 and C2 are the constants of integration. So the values of constants obtained as, you know that at x is equal to 0, y is equal to 0. Substituting these values in equation 1. In equation 1, x is equal to 0, y is equal to 0. Substitute these values in this equation. So 0 is equal to C1 cos 0 degree and sin 0, and C1 is equal to 0. Similarly, when x is equal to L and y is equal to 0. X is equal to L and y is equal to 0. Substitute when x is equal to L and y is equal to 0. So 0 is equal to C1 into cos. In place of x, substitute L square root of P by EI, and C2 into sin L into P by square root of P by EI. So now find out C1 from equation. This value is 0 and C1 0. So sin C2 into sin L into square root of P by EI. So now C2 is, find out C2 sin L into square root of P by EI. From equation 2, the C2 equal to 0. So C2 to be equal to 0, as also C1 is equal to 0 and y is equal to 0 from equation. So it indicates that the column has not bent at all, or bending of the column will 0. But it is not true. See, sin L, sin of L into square root of P by A is equal to 0. So for this, calculate this square root of L into square root of P by EI for 0, 5 and 2 pi and 3 pi values. So taking the least significant value. So the significant value you take, so that is pi. L is square root of P by A is equal to pi. So now you can find P is equal to pi square EI by L square. Squaring on both sides. Squaring the both sides. So after squaring, what will happen here? L square into P by A is equal to pi square. Now, from this equation, PL square is equal to pi square EI. So the buckling load or crippling load P is equal to pi square EI by L square. So this is the equation how derived. Whenever the given column end conditions are, the both ends are hinged. So like this, how to derive the buckling load equation. So suppose in second case, one end is fixed, other end is free, or both ends are fixed. If both ends are fixed, like this. So in this case, it may vary the load, buckling load. So first you have to derive based on the given condition and then apply this formula for our problem. So in examination they will ask, find out the buckling load. So they will give fractional rigidity value E, EI, or moment of inertia or E, and the length also they will give, the length of the column. So pi square EI by L square. So finally we got pi square EI by L square is whenever the column is both ends are hinged. So like this you have to derive the equation. So these are the references I have taken. One is as Ramamurthu, Strength of Materials, the title of the book, and Dhanpati Rai Publishing Company, and then R.K. Bansal, that is a textbook of Strength of Material, Lakshmi Publications, and then R.S. Kurmi and Gupta. So the Strength of Material, the title of the book, and publishers are Hudson and Co. So these are the references I have taken for this PPT. So take any one reference book and further clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.